Okay, so I'm Leandro Rímolo. I'm from São Paulo, University of São Paulo, Brazil, and I'm going to present my project, which is called a semi-automatic pipeline for investigating light curves of BE stars. Well, this is a project based on the VDD scenario, in which mass is injected from the surface of the star and is diffused by viscosity to the outer parts of the disk. The VDD scenario in steady state have been successfully tested for several BE stars. However, BE stars are dynamical and variable objects. And one of the main questions regarding the VDD scenario is the origin and magnitude of the turbulent viscosity. And several light curves of BE stars are available from service now and services. The object of my work is to study the viscosity through the photometric light curves of hundreds of BE stars available. As everybody has, I also use the radiative transfer called H-dust, as some people have known in this conference. And these are very beautiful pictures showing H-dust in action, one from Ackernar and the other for Zeta Tal. And this is an interesting picture useful for this work, which shows the loci of formation of different observables in the disk. And we see that visual observables like V band or H band usually form in not much more than 2 or 3 stellar radii. So most part of what we observe in visible is formed close to the star. As I mentioned, several surveys are available. These are light curves from, these are surveys available, surveys of light curves of BE stars. OGO, which will function between these years from 1996 to 2009, observed in I bands, dense coverage. These figures are from OGO survey, and we see I magnitude against time. And also they observed V and B magnitudes sparse coverage. Eros and Macho surveys are also surveys, and other surveys like Super Macho are interesting, but they only have one filter, and ASAS has only a few bright stars. And we see these very remarkable features of these light curves. So these are variabilities of BE stars, some very interesting, like this one. Manny-Kent, as an example, Manny-Kent in 2002 and collaborators selected from the OGO-2 light curves just from the small Magellanic Cloud 1,056 BE candidates from this survey, and like 15%, 124 out of these 1,056 were these type 1 light curves or bumpers like these ones, when we see a rather quite stationary state and then a sudden increase, excess, and then a decrease, like making this bump. In our interpretation, this is like we interpret this as a single mass injection, and then a single very big mass injection from the star to the disk, and then a reaccretion of the material, mainly from the disk. So we observe these kinds of bumps. This is as we saw this curve first here. Where's him? We saw that he models from a disk in a very extensive region. But in my case, I'm only interested in no more than like 20 stellar radii. This is equivalent to saying that the pressure, force due to pressure, is much less than the force due to the gravitational field of the star. So pressure is not much relevant. This is equivalent to saying that the scale of height is small. So the angle, opening angle is small. We here have a figure of how the density distributes in this region of the disk. There is a line, white line here, but it's hard to see, but this is the scale of height, the double of it. So in these regions, the disk is quite thin. So we're dealing with thin disks here. We end up with this equation for the evolution of the surface density of the disk. Surface density sigma, which is the density integrated in the height, is given by this equation. This is a source term. This is a delta function. So the masses injected in a cylinder of radius r inject, which is very close to 1. This is very close to 1, very close to the star. And this is the viscous time scale, which is a function of the alpha parameter of Shakura-Sunyaev, which is describes the viscosity. And these are parameters of the star. So actually this temperature is temperature of the disk, which is 60% of the temperature of the star, mass of the star, radius of the equator of the star. And this sigma injection is the surface density that will be, this sigma injection is this point. When mass begins to be injected, this point it starts to reach this point. It tends to this stationary state. So it is the surface that is reached after a constant mass injection rate. This is a other way of saying mass injection rate. And this is the typical mass decretion rate, which is a function of this. Studying these equations, we see that the variable mass injection, we here see a movie. This is a light curve, a very complicated light curve, and we imagine that we are seeing like this. A variable mass injection. Sometimes we see an increase in surface density and decrease. And here we are plotted several values of the radius of injection, so it's not a big deal. It doesn't change much. We just have to, well, they are plotted together. Just this region are different. Is different. And here we see a very recent work by Alex Karsiofi and collaborators, which was the first determination of the alpha parameter based on light curves using this formalism. And they found that alpha was close to 1 for this dissipation. And we see that other dissipations, if a lower alpha generates a not so fast, okay. The greater the alpha, the faster the dissipation. We see here what happens with an alpha with the one tenth of the value. We see this with 1/10 of the value, the density is still big, while in the other case, the disk disappears very much faster. Continuing our study, we see, let's see what happens if we have a disk that has been a constant mass injection rate, one for 30 days and the other for 2 years. We see here the light curve and here the movie. One almost disappears very fast. The other that begins with 30 days was being injected for 30 days, and the other takes longer to disappear, because if we return, we see that it has a reservoir of matter that still makes we see the disk, and the other disappears. So when we look to the computed 5 minutes, and when we look to the dissipation, we see that dissipation looks slower than the other. When we normalize them, we are certain that it is slower. So we see here in light curves, we see this effect here too. So we see different time, different build-up time leads to a slower dissipation. Also, if we have two different mass injection rates, the one with greater mass injection rate seems to take longer to dissipate. And therefore, we found this law more or less adjusts for every dissipation in light curves. It is an exponential decay. And we have here an excess, and here's a parameter that depends on radiative transfer. This is the viscosity timescale. And these two parameters, they depend on the central star, temperature, radius, and mass, inclination angle, this injection surface density, and the time it was being injected. This parameter is this magnitude of the central star without the disk, and this depends only on the characteristics of the central star. So let's turn now to the Yogo-1 light curves as an example. We now have I-band, so I put I-band here. And therefore, based on these dynamical models, we derive a following chain of procedures or pipeline for determining the alpha parameter for the stars with semi-automatic using light curves. From color, distance, and reddening, we know the central star, like we know more or less radius, mass, and the temperature. Then we have alpha tau, which depends viscous time scale for these inclinations. We don't fit very well with edge-on cases, but we can exclude them by color information. From the height of the light curve we see here, we can see this excess, which is this light height. We can invert this to get the sigma, the mass surface injection, surface density. We invert the equation. And from our models, we see here that what we saw, what I changed. Here I have different surface densities. This is a bigger, this is smaller, and even smaller. And as the time of injection takes it's longer, this appears to dissipate slower. And with these parameters, we can find the alpha parameter like this. We fit this dissipation with a power, this exponential decay. And with our models, with our AI, this parameter, which we tabulated, and this one given by the central star from color, distance, and reddening, we find the alpha parameter. So here, we are trying to run because this figure was generated with a few models. We're now trying to generate more models, but let's try to make some examples, but don't trust too much on these results. But alpha tau for this light curve, this is not a good example. This is actually the viscous time scale of 28 CMA. But I found for this time, this A parameter, we see like 3 years. What is this? No, 1 year. And 1 year we see between 1.5 like this. With this parameter we find this alpha for this light curve. For this one we find 0.3 or more because I can't see exactly how it began. So if it had begun after this point, then the alpha is bigger. This one is not a good one, but it's also a 0.3. You can interrupt me if you. And this is quite a. I put it here to show that some are very complicated. Some doesn't look like just one outburst and then a dissipation. It's more like a complicated one. And this is 28 CMA. This is the region Alex Karsiofi and collaborators used to adjust the model, and I found this value of alpha, which reaches 1, more or less. This is the fitting. I exclude this small outburst here, and I tried this other part that it was not modeled, and I found also alpha more or less 1. So, thank you, everybody.
Question for Leandro?
You tried to model light curves of B-star candidates.
Yes.
Have any of them been confirmed as B-stars by spectroscopy?
No, as far as I know. But I think some have, not these articles, but I think I have seen some with H alpha, some measurements in UC emission, but not all of them. So, some are just selected by variability and, well, by their position in HR diagram. So we know that are B stars, and then they are variable, and in the kind of variability that is erratic, not like a binary. Yes.
Just to answer that question, many of these stars were found by Macho, and then they were interpreted as candidates for gravitational lensing, and the criteria were that a symmetric light curve and a small color term. And all the stars of which spectra were taken were BE stars.
Yeah, so this is nice work because I think, as you pointed out at the beginning of your talk, you can't always run big numerical models for every time you want to try to hit things. When we have a large amount of data, we want to try to survey it. But I think it'd be nice to come with even simpler scaling relations that one could just use as the back of the envelope. And this could really start with just this diffusion time, where you just, if you know the alpha value, you can actually compute. I think I did it up with scratch paper here, and it comes out to something like the orbital time scale times the rate. You know, if you assume a typical value for the sound speed of the star, 25 kilometers a second, orbital speed of 500, it comes out to something like the orbital time scale times 100 divided by the viscous coefficient. So that's a kind of simple scaling relation that one can get. I think you can do a little bit better than that with sort of like this Green's function solution that you have for disk spreadings. You just calculate that and then your model, you actually solve the time-dependent diffusion equation, but you're doing it for an impulsive initial mass. So it's a lot like this Green's function solution. And so it'd be nice if at the end of the day, one could kind of quote this kind of scaling relation for the time scale for the dissipation. And I think it's going to basically come out to a number that you can write in terms of basic physical parameters, like the radius of the star, the ratio of the sound speed to the orbital speed, and the alpha coefficient.
See, that's what we started with, but unfortunately it's more complicated than that,
Well,
because
but then
it
you
really
should just
depends
compare
on the previous history of this.
Well, but in these impulsive events where you have something shooting up like that, what's the history of the disk? There's no disk.
Yeah, in this case there's no disk.
Well, that's what I'm trying to say,
But
sure.
you see, one shoots up, comes back down immediately, is a short time scale. The
Right.
other shoots up, stays a while, fills the disk, and then
Right.
comes down much slower.
Well, the Green's function is the ultimate piece of information of what happens with the delta function. And then you have to integrate the Green's function over some time history of adding mass. So in principle, that is what you're doing when you're solving your diffusion equation. What I'm trying to say is that when you have these simple results, it'd be nice if there were simple scaling relations, so that when you look at a plot that is like that, like the case with this impulsive mass loss, as soon as you see the decay time scale, you look on your little chart and it says, oh, that's got to be alpha of the order of this. I mean, it may not get exactly accurate, But for surveying the broad trends with different spectral types and different stellar parameters and stuff, it seems like that would be a very useful thing to do, even one step simpler than what you're doing, which is one step simpler than the big hydro 3D, H-disk modeling. So all I'm trying to say is that it's very good to have back of the envelope scaling relations that help orient you in the big parameter space. And so I think what you've done there is wonderful. I just encourage you to also not just connect it onto the very complicated models, but also to connect it onto a simpler scaling relation.
Okay, I think we have to move on. Thanks again.